Good morning, everyone. I hope that you had a great weekend and you're all doing good today. We're looking today on page 11 of your current lesson handout, and we're going to be covering two short lessons. The first lesson deals with the polarization of light and polarization of electromagnetic radiation in general. And then the second little lesson we're going to be looking at is something called the photon model of light. So to begin with, we just finished studying diffraction and interference of light. And diffraction and interference of light shows that light is a wave. When you start talking about diffraction of a wave is when a wave goes through an opening and it spreads out. If you pass particles through an opening, the particles won't spread out. Interference of a wave happens because two waves exist in the same space at the same instant in time. And that's something that particles certainly cannot do. So in the end, we conclude, based on these experiments, that light is a wave. But there's two different types of waves, and I want to review them with you briefly here. There are what we call transverse waves and longitudinal waves. And in a transverse wave, the medium, whatever is waving, whatever is oscillating, whatever is jiggling, the medium is moving perpendicular to the direction of the energy in the wave. Whereas in a longitudinal wave, whatever is oscillating or moving back and forth is moving in the same general direction as the energy of the wave motion. As an example, here's a model of a transverse wave. What is happening is the medium on the left is being forced up and down, but the energy moves in this direction. And those two directions are at 90 degrees to each other, which means it's classified as a transverse wave. In a transverse wave, the medium and the energy are perpendicular to each other. When we take a look at a longitudinal wave, what's happening in this longitudinal wave is the medium is being forced back and forth, and as a result, the energy moves to the right, and that's what makes this a longitudinal wave. The direction of oscillation of the medium is parallel to the direction of the motion of the energy. Classically speaking, in Physics 20, you're probably taught that this is an example of something maybe like a water wave, whereas this is an example of something along the lines of a sound wave. Well, again, like much of what we do in Physics 30, we're trying to tie all of this knowledge to what we call electromagnetic waves. In this particular lesson, light. And we'll have to talk a little bit later today about what the medium is that's oscillating in light in order to make this transition from mechanical waves to electromagnetic waves. Now, there is one phenomenon that a transverse wave will undergo or experience, but longitudinal waves cannot experience, and it's called polarization. When you take a wave, if it's a transverse wave, and you force the medium to oscillate in only one plane, then we say that we have polarized the wave. And only transverse waves can be polarized. The basic reason is that longitudinal waves are always only oscillating in one plane. They always oscillate back and forth. Now, how is it that we can have a transverse wave oscillating in different planes? If I go back and take a look at this diagram or this representation of a transverse wave, this is how it's always drawn on a board for you in school. You have the wave causing energy to move to the right, and the medium moves up and down. But the fact of the matter is, instead of having the medium moving up and down, what we could be doing is taking the medium and moving it in and out of the board. Now, it's not, but if I were to take the medium and pull it in and out of the board, then I would say that it's oscillating in a horizontal plane. Right now, it's oscillating in a vertical plane. Well, there's nothing to say that it can't be oscillating in both planes. That would require some coordination on my part, but I would have to grab a hold of that medium on the left and move it up and down while at the same time moving it in and out, kind of in a circular fashion. And the result is that some of those particles at some point in time are going to be moving up and down, some are going to be moving in and out. Now, I'm going to use an analogy here. What we're looking at is a transverse wave that's coming out of the board or out of the screen towards you. And you can see all of these arrows indicating the direction that the wave is oscillating. In order for this to kind of make sense, I hope you can wrap your head around this. I would like you to imagine that you were holding one end of a skipping rope. And that skipping rope is going into the screen that you're watching this on, and it's going through the screen, and I'm behind the screen holding the other end of the skipping rope. And what we're doing is twirling the skipping rope around, and at times the skipping rope is moving to the left and to the right. And at times the skipping rope is moving up and down, and it's moving in this direction. It's moving in all of these directions because we're forcing it to move in a circle. So sometimes the rope is on the left, sometimes it's on the right, sometimes it's on the top, sometimes it's on the bottom, sometimes it's over here, sometimes it's over here. It's oscillating in all of these different planes. And now what we're going to imagine happens is these two barriers that I have on the left and the right start squeezing in. And no matter how much they squeeze in on that skipping rope, you and I are going to continue to try to force that skipping rope to move in a circle as much as we can. When those two barriers get a little bit closer, as soon as the skipping rope hits this barrier and this barrier, it can't move past those barriers, but it continues to move up and down because we're doing our best to move it in a circle. And the end result is, as these barriers get closer and closer and closer together, the rope ends up moving only up and down. You and I are doing our best to cause it to move in a circle. But because the rope is in between these two barriers, it can't move in a circle, so all that happens is it moves up and down. This would be now a polarized wave. It turns out, so now we're going to make the leap to light. It turns out that in light, which is an electromagnetic wave, there are two different waves working together, an electric wave and a magnetic wave. And when you take a light wave that has no polarization, which means it's oscillating, those electric and magnetic waves are oscillating in a whole bunch of different directions. When it passes through a vertical polarizer, which contains a bunch of openings that are vertical, those openings are not small enough to cause diffraction. When that wave passes through that vertical polarizer, only the part of the wave that was oscillating vertically makes it through the polarizer. If I were to take a second polarizer, one that is oriented horizontally, then the net result is that you're going to get no light, because the second filter or polarizer is going to stop anything except for horizontal light, but there is no horizontal light because the vertical polarizer eliminated that. So you get no light. Now I'm going to show you a demonstration here involving what are called polarizing filters, or sometimes they're referred to as Polaroid filters, named after the company that invented them. So we're looking at here an old filament style light bulb. The filament is the part that's glowing orange. It's where my finger is pointing at right now. And then I have a Polaroid filter, and when I put the Polaroid filter in front of the filament is still visible, but the whole color is washed out a bit. It's not as bright, it's more orange here. So it is filtering out some of the colors, and you can tell by looking at the background that the background is quite dark and gray compared to without the filter. So now I have two filters. They're overlapping each other, and you can see where they overlap, the brightness of the light is not really diminished that much more than it was with just one filter. That's the image through one filter, this is the image through two. It is diminished a little bit more because of the second filter, but not significantly. Now both of these filters are aligned in the same way. What that means is that each of these filters is blocking out all of the light to reach the camera, except for light that is oscillating towards the top of your screen and the bottom of your screen. So these are both aligned vertically. And that would mean that if I turn them 90 degrees, they're both aligned horizontally. And if they're both aligned horizontally, they're blocking out all of the light except for the horizontal here, and here they're blocking out all of the light except for the vertical. If I were to take one of the filters and start turning it relative to the other one, more and more light gets blocked out until eventually what happens when they are at 90 degrees to each other, in theory, what happens is you get all of the light blocked out. You can still see, obviously, some of the light making its way through. It's probably going to appear as a bluish color on the video because blue light is the most energetic of the colors and it has enough energy to make it through these filters. These filters are not perfect. But this definitely provides evidence for the fact that light is a transverse wave. So I hope that demonstration drives home what's important about polarization. When you have the two filters at 90 degrees to each other, you're going to get, I want to say, zero transmission of light, but the Polaroid filters that I was using in the demonstration are not perfect, so you may have got a little bit of visible light making it through. The most important aspect of polarization of light is that it demonstrates that light is a transverse wave. All right, so now that we've convinced you that light is a wave because it diffracts and interferes, and that the type of wave it is transverse because it undergoes polarization, we're going to look at the other side of the coin, which is that light can also be thought of as a particle. And we'll talk more about what that word particle means in this sense. But this little lesson is on what we call the photon model of light, or in general, the photon model of electromagnetic radiation. And I believe this is on page 12 of your handout. So there are some things in the universe that we observe, and no matter how much we wrap our head around these things, it's impossible to explain them by assuming that light is a wave. It just does not make sense to assume light is a wave for these things. One of them is called the photoelectric effect, which we're going to learn about in detail over the coming days. And another one is called the Compton effect, which we are also going to study in detail. The only way to explain these phenomena is to assume that when electromagnetic radiation is either emitted or transmitted, which means moves from one place to another, or absorbed, which means the energy is transferred to an object, the only way to explain these phenomena is to assume that when light travels, it exists as little tiny, tiny, indivisible bundles of electromagnetic radiation energy. And these particles, which have no mass, which is why I like to use the word particles in quotes, these particles of energy are referred to as photons. Don't confuse the word photon with proton. So what we're talking about here is the idea that electromagnetic radiation is quantized. Quantized means it comes in only certain lumps. We have already studied something in this course that is quantized. Charge is something that is quantized. We have learned that the charge on an object could be 1.60 multiplied by 10 to the negative 19 coulombs. And if it were a positive charge, the explanation for that would be that the object is missing one electron. We have learned that you could have a charge on an object of positive 3.20 multiplied by 10 to the negative 19 coulombs. We have learned that you can have a charge of 4.80 multiplied by 10 to the negative 19 coulombs. In fact, you can have a charge that is a multiple of the elementary charge. N here is a natural number. It's 0 or 1 or 2 or 3. And the explanation for that is that things are charged because they are missing electrons or they have extra electrons added to them. And you cannot have part of an electron. And that idea that you cannot have part of something is crucial to your understanding of what it means to say that thing is quantized. It can be one of them or two of them or three of them, but I can't just have any amount of charge on an object. It's got to follow this rule. Well, that's what we mean when we say that the energy emitted in the form of electromagnetic radiation is quantized. So Max Planck came up with formulas that we use to calculate the energy of a single photon of radiation. And you can use these formulas for any type of electromagnetic radiation. Radio waves, microwaves, radar, infrared radiation, visible light, ultraviolet light, X-rays, gamma rays. It will work for all of them. The first formula says E is equal to HF, and H is a constant. It's now named Planck's constant, and we'll look at it in a second. Or you can use E equals hc over lambda. In the formulas, E is the energy of one photon. H, of course, is Planck's constant. F is the frequency of the radiation. Lambda is the wavelength of the radiation. So if you know the frequency, you can use the formula on the left. If you know the wavelength, you can use the formula on the right. Yeah, let's take a look at the first example. How much energy is carried by a photon of each of the following? We have red light of wavelength 680 nanometers. So we're going to use the formula E equals hc over lambda. Now, when we take a look at your formula sheet, on the constants table of your formula sheet, you will see Planck's constant, and you will see that it is given in two forms. 6.63 multiplied by 10 to the negative 34 joules multiplied by seconds, or 4.14 times 10 to the negative 15 electron volts multiplied by seconds. This allows you to calculate energy of a photon in either joules or electron volts. So in this example, what I would like to do is I would like to calculate the energy of the photon in three ways. The first thing we're going to do is calculate it in joules using the formula. So the energy of a single photon will be Planck's constant, which is 6.63 multiplied by 10 to the negative 34 joule seconds, multiplied by the speed of light, divided by the wavelength, which is 680, and it's in nanometers, so we can put times 10 to the negative 9 meters. And I'm putting the units in here to show you that the units are going to give us joules in the end. The seconds will cancel with the seconds on the top, the meters and the meters will cancel, so we'll be left with energy in joules. .63 multiplied by 10 to the negative 34 multiplied by 3 times 10 to the 8 divided by 680 multiplied by 10 to the negative 9 gives us a very tiny amount of energy, 2.925 multiplied by 10 to the negative 19 joules. And that's the energy of a single photon of red light. Let's calculate now the energy of the photon in electron volts. Well, we can go back and we can use hc over lambda. This time we're going to use the other value of Planck's constant, which is 4.14 multiplied by 10 to the negative 15 electron volt seconds times the speed of light, and then divided by the wavelength. And let's see what we get this time. So 4.14 multiplied by 10 to the negative 15 times the speed of light divided by 680 nanometers gives us 1.83 electron volts. And back, I would say 6 to 7 weeks ago when I first introduced you to electron volts, I said that electron volts are a unit that we would want to use a lot of the time because they're easier to work with. And it's just easier to say that the red photons have an energy of 1.83 eV than it is to talk about them having 2.93 multiplied by 10 to the negative 19 joules. Of course, if you wanted to know the energy in electron volts, you could have calculated the energy in joules like we did, and then converted that energy in joules to electron volts by using a ratio, or for what many of us is just common sense. But if you use a ratio, you write 1 electron volt is equivalent to 1.60 multiplied by 10 to the negative 19 joules. That ratio has to equal X electron volts over the energy that we've calculated, 2.93 multiplied by 10 to the negative 19 joules. So now you're going to take that energy in joules that we had, which is actually 2.925 times 10 to the negative 19 joules, and divide by 1.6 multiplied by 10 to the negative 19, because that's how many joules there are in a single electron volt, and you get 1.828125, which is 1.83 eV. Now, you don't get exactly the same number that we got when we used the other form of Planck's constant, because those two constants are not exact. I believe instead of 4.14 times 10 to the negative 15, I think it's 4.136. There's other factors at play here that affect the answer, which means that potentially, depending on how you do these questions, you could get a slightly different answer than somebody else. Now, I said that I was going to show you one more way to do this, and I'm spending an awful lot of time on this first example because it's important. We can use hc over lambda equals energy. Now, a common energy unit is electron volts. A common wavelength unit is nanometers. A lot of the time we're working with nanometers and we want to figure out how many electron volts a particular photon has if we know the wavelength in nanometers. Sometimes we will know the energy in electron volts of a photon, and we want to know the wavelength in nanometers. Well, it turns out that the product of the energy in electron volts and the wavelength in nanometers is 1242. I am just showing you a shortcut. This is not on a formula sheet, but you will remember 1242. And this is what I am going to use throughout most of the remainder of the examples. If we go back and we look at this first example, the wavelength was 680 nanometers, which means that the energy multiplied by the wavelength, which is 680 nanometers, has to equal 1242. So to find the energy, I just take 1242 divided by 680. And by the way, if I knew the energy, I would take 1242 divided by that to get the wavelength. 1242 divided by 680 is 1.83. That is a huge time saver, everybody. I'm going to be using that. If you want to substitute numbers into the formula, that's fine. You can do this, and I'm not trying to dissuade you from it. If I wanted to know the energy in joules, I would still use the 1242 trick to get the energy in electron volts. Then I would just convert it to joules. And I get 2.92 times 10 to the negative 19 joules. Which, by the way, if you take a look at what we got 2.93. This goes back to the whole idea that these constants are not exact. So now let's take a look at the next question. What is the energy of a photon of green light if the wavelength of green light is 540 nanometers? Well, we're going to use E equals hc over lambda, but hc is 1242. This is, I guess, what I'm saying, the formula that we can use instead of hc over lambda. So the energy will be equal to 1242 over 540, and that will be an answer in electron volts. So the answer is 2.3 eV. If you wanted to know that in joules, then you could convert that to joules, knowing that 1 electron volt is 1.6 times 10 to the negative 19 joules. What is the energy of a photon of violet light? I'm not even going to write anything down here. It's going to be 1242 divided by 420. 2.96 eV. Interested in knowing how many joules that is? Well, convert it to joules. Look, I'm not saying you can't use this formula, hc over lambda. There may be the odd person who's watching this that will want to actually put in the number on your formula sheet for Planck's constant, the value of the speed of light, and the wavelength in meters. I'm just telling you there's a lot quicker way to get to our answers. Now we have ultraviolet radiation with a wavelength of 20 nanometers. Well, we would take 1242 divided by 20. And we get a whopping 62.1 eV. So just to kind of summarize things here before we deal with the remainder of the examples, when you have a light bulb that has a red filter on it that only allows the wavelength of 680 nanometers to go through, the fact of the matter is what's happening is that light bulb is spitting out like little bullets from a machine gun. Little tiny bundles of light energy, and each one of those little bundles of light energy, which is called a photon, has an energy of 1.83 eV. When you take a look at the photons emitted by a green light bulb, I draw them bigger. Now, a photon doesn't necessarily have a size. That's not what I'm suggesting. I'm just representing the size of it to mean energy. So we calculated it was 2.30 EV for the green. The blue light, which has even more energy on the electromagnetic spectrum, is up at 2.96 EV. And then I have an ultraviolet light source here. Now you can't see UV light, so it doesn't have a color. I've just chosen to draw these photons using kind of a grayish color, but their energy are 62.1 EV each. Let's take a look at the next question. How much light energy is carried by 1200 photons of a certain wavelength? Well, the idea here is you can calculate the total energy carried by taking 1200 multiplied by the energy of one photon. If we calculate the energy of one photon, I would say that's, at this point in time, as easy as taking candy from a baby. It's 1242 divided by the wavelength in nanometers, which was 670, which gives me 1.8537 EV. The answer to this question is going to be 1200 multiplied by 1.87 EV. Which gives me 2224 electron volts And of course, you can convert that to joules. I'm not going to, every time we convert EV to joules or joules to EV, set up a ratio. That might be something you're going to have to go back and review. So 3.56 times 10 to the negative 16 joules. A very common question that students are going to ask, and you're not here to ask it, so I'll try to anticipate it, is how do you know which unit to use? Well, I guess it depends. If you were working on a multiple choice question and all of the choices had joules, then you would want to work towards joules. Otherwise, it's entirely up to you. Number 3 gives you the information that we have a photon with a certain energy. We're asked to determine what type of electromagnetic energy is it. I would make the recommendation that you never want to worry about frequency. You never want to worry about energy. You want to think in terms of wavelength. Most of us have gotten used to organizing electromagnetic categories based on wavelengths, not frequencies or energies. So if I cross multiply here, I get E times lambda equals hc, which means that lambda equals hc over E. But again, hc is 1242. By the way, I might as well put the units here. The units of this 1242 are electron volts times nanometers. So we're getting 3,105 nanometers. When you're talking about thousands of nanometers, you're talking about infrared radiation. Red light in the electromagnetic spectrum ends at 700, and as you get past 700 into the 800 or even thousands, you're dealing with infrared. So the answer is 3,100 nanometers. Which is infrared radiation. The part of the electromagnetic spectrum that has an even longer wavelength than infrared would be in the microwave region. You should know microwave is the millimeter to centimeter region. If I multiply this wavelength that's in nanometers by 10 to the negative 9 to get it in meters, that is nowhere near a millimeter. So it's a longer wavelength than visible light, but it's definitely shorter than microwaves. And what that means is it's infrared. Your assignment is to complete the problems below, which are all from your textbook, but I've just put them in your lesson handout to make it a little bit easier for you. It has occurred to me that in all of the examples that we did today, we were using E equals hc over lambda, but there is another formula, E equals hf. There's no shortcut with the E equals hf formula. If you want to know the energy in electron volts, you just have to make sure that you put in Planck's constant in electron volts, which is 4.14 multiplied by 10 to the negative 15. If you wanted to know the energy of a photon using the second formula that you're looking at here, but you want the answer in joules, well, then you would load in for H 6.63 times 10 to the negative 34, because that's Planck's constant in joules. Just a reminder, tomorrow is a Google Meet day, so if you have any questions from today's lesson or from Friday's lesson on interference and diffraction, that's your chance to get those questions answered. As well, assignment number 4 is due tomorrow, so hopefully you haven't left that till today. You've already got started on it and potentially even got it done. As well, for assignment 4, remember that you have to watch the supplemental video, which is linked from your Google Classroom page. Have a wonderful rest of the day, you guys, and we will talk to you soon.